Swayam Prabha. Digital India. Educated India.
Welcome to the DTH course on micromachining. In the last lecture, we discussed electrochemical spark micromachining, an overview. Here we are going to discuss part 2 of the same. What we have done in the last lecture is as follows: introduction to electrochemical spark micromachining and setup development, where we discussed the various setups developed at IIT Kanpur and other institutions across the globe. Then we discussed theoretical estimation of temperature in ECSM process and ECSMM process, and then metrology techniques for the measurement of the micro features created over there, say microchannel. This technique can also be used for the measurement of micro dimples and micropillars and so on. Electrochemical spark micromachining process performance evaluation also we discussed. It can be evaluated based on the depth of the features created, width of the feature created. If it is a channel, then overcut of the on the feature created. Now we are going to discuss performance analysis of ECSMM process. Parametric analysis of the process. As we can see here, stars are the experimental points and this is the simulated curve. Width of heat affected zone, we have discussed what is the heat affected zone. So, width of heat affected zone is affected by the voltage that is applied across the electrodes, and you can see these points show the actual experimental results, and this is the fitted curve, and we can see clearly that the width of heat affected zone is increasing as voltage is increasing. So, effect of voltage on width of heat affected zone. Same way here we can see variation in depth of microchannel for 55 volt, and this is the distance from the reference point and this is the depth. Now you can see here this is more or less constant over here as long as distance from the reference is concerned, except the first starting point where the depth is more. Then we have the width of the channel for table feed, that is the feed rate, and as you know, if the feed rate is increased, then definitely material removed will decrease, because time available will be reduced and the total amount of the material removed is decreased. That is why width of the channel is more or less continuously decreasing with the table feed. Now here width of the heat affected zone is also reducing with increase in the table feed, but somehow the experimental points do not show the very consistent trend, and that may be due to some variation in the experimental machining conditions. So, this is the work taken from the thesis of Priyadarshini. Parametric analysis, theoretical results, width versus voltage and width versus sodium hydroxide electrolyte concentration. You can see here this is the voltage and this is the microchannel of the width. It is continuously increasing with increase in the voltage, but beyond a certain value of the voltage it starts decreasing due to the various regions, and these are the results for different feed rates, micrometer per second. Same way electrolyte concentration percentage and microchannel width, it is continuously increasing up to a certain point of concentration, because I have mentioned in case of electrochemical micromachining also, that the conductivity of the electrolyte increases up to a certain concentration, and if you increase the electrolyte concentration beyond a certain point, then conductivity starts decreasing, and that is the result that the microchannel width is also decreasing beyond a certain value of the electrolyte concentration. Now, this is very unique and very interesting result that you will find over here. It says parametric analysis while working with both polarities, that tool is positive and it is negative. Now, very interesting results. Shifting of sparking zone between electrodes, that is cathode and anode, and sparking at cathode and sparking at anode. This is Mr. Adhikari's work, which has been published in renowned journals, international renowned journals. You can refer them. Now, here you can see this is the anode and this is the cathode, and both of them are having the workpiece over there, and depending upon the size of the electrode, you will find that sparking is taking place, and sparking may take place at the anode, sparking may take place at the cathode, depending upon the size, because we already know that at cathode hydrogen is evolved, at anode oxygen is evolved, oxygen bubbles are there, and across those bubbles the sparking takes place, as we will see. Now, here you can see this is the sparking at the cathode is taking place, and anode there is no sparking, because no sparking at anode. Shielding by oxygen and vapor bubbles increases resistance over here, and at a certain point the dielectric, this gas acts as a dielectric and breaks down. Now, you can see here shielding by hydrogen and vapor bubbles increases resistance, and sparking at the cathode is stopped. Here sparking at the cathode is taking place, here sparking at the anode is taking place. Setup is the same, except that some conditions are changed, and this feature has a lot of opportunity to do further research activity, research work to explore its potential. It is very interesting, and this was first time when this paper was published that it was shown that the sparking can take place either at the cathode or at the anode, depending upon the size of the cathode and anode and their relative sizes and the machining conditions. Bubbles generation at both electrodes take place. You can see over here, this I have mentioned to you. This is the workpiece which is electrically non-conducting, this is the electrolyte, a small size cathode is there. So, bubble generation is there, and sparking will take place here, and this is the anode which is the larger size, and bubble generation is here also. Both the electrodes can be simultaneously used as tool. Electrochemical spark machining with direct polarity, dP stands for direct polarity and Rp stands for reverse polarity. In ECSM, WdP and Rp, auxiliary electrode also may be of small size. Here it is shown larger size, but both can be of the small size. However, if there is sparking at cathode in reverse polarity, sufficient potential is not available at anode tip for machining. That means if sparking is taking place, here sparking will not take place, and vice versa. In reverse polarity cuts quartz plate at faster rate compared to direct polarity, right. So, it says which is working faster, but produces higher overcut and higher tool wear. So, one has to look into the merits and demerits of reverse polarity and direct polarity, and accordingly decide which polarity you should use for sparking to take place and for creating micro features. Tool wear in both polarities is shown over here. In direct polarity, material is removed from cathode by melting and vaporization due to heat generated by sparking, because sparking is taking place at the cathode. So, that is there, but tool wear is negligible. Material, because why tool wear is negligible? The reason is material is deposited on cathode, by electrochemical reaction, because from the anode material is being removed due to the electrochemical reaction, and this gets deposited on the cathode. That is why tool wear at the cathode is negligible as mentioned over here. In reverse polarity, material is removed from anode, that is the workpiece. In this case, sorry, not the workpiece, but anode is there because workpiece is electrically non-conductive. By melting and vaporization due to heat generated by sparking at the anode. In this case, sparking is taking place at the anode, and there is a high rate of tool wear, because at anode tool wear is taking place and material is also being removed from the anode, as we already know from the electrochemical machining on Faraday's laws. Material is removed by anode by electrochemical reaction like this. Effect of voltage on penetration rate in both polarities. This is when tool is negative, penetration rate is continuously increasing in a certain trend, with a certain trend as you increase the voltage, and which is obvious because as voltage is increased, current flowing is also increased, current density increases, so material removal rate also increases. It is in millimeter per minute, that means linear material removal rate. Again, this is the linear material removal rate, that is the penetration rate. As voltage is increased, this is the tool is positive, as voltage is increasing, material removal rate or penetration rate is also increasing. Although at a particular voltage in both the cases that there is large deviation with reference to this curve, simulated curve over here. Almost same trend in both the cases, that is reverse polarity and direct polarity. Now let us discuss effect of voltage on average kerf width in both polarities. As you can see here, average kerf width versus voltage when tool is negative, the kerf width is also continuously increasing with the voltage, because we already know that as voltage is increased, material removal rate is also going to increase, and as a result of that kerf width is also going to increase as shown over here. Now in the case when tool is positive, again as the voltage is increasing, kerf width is also increasing. Here also it is more or less continuously increasing, although there is slight difference in the trend of negative tool and positive tool, or the direct polarity and reverse polarity. That may be due to some other reasons which we are not discussing here. Now effect of voltage on average surface finish in both polarities. Now you can see average surface roughness value Ra in terms of micrometer is given over here, and this is the voltage, and as voltage is increasing, surface roughness value is increasing, which is obvious because due to sparking the craters being formed. With the higher voltage will be having deeper or higher depth, they will be having more depth, and as a result of that surface roughness value will increase. If the voltage is low, definitely depth is low and surface roughness value is low. Same trend is there, that with positive tool the average surface roughness is increasing with increase in voltage. Although there is slight difference in the trends, in the first case it is continuously increasing, it is trying to flatten down further, but all this depends upon certain machining conditions also. So slightly different trend in both cases, one increasing while another stabilizing in case of positive tool sparking, that is this one. More heat is generated as compared to negative tool sparking, that is what shown over here. Experimentation, transient current and temperature measurement methodology. This is very important part, because when you want to study the scientific aspects of electrochemical spark micromachining, you should study the transient current and transient temperature. So how to measure them is important. Some observations and inferences are given over there. Transient current measurement, current contribution due to sequential events, Now here just see how this current measurement was done at different points. Now T1 time, T2 time, T3 time, T4 time. Electrochemical action takes place during the first T1 time, growing hydrogen bubble during the T2 time, and then virtual off during the T3 time, because bubbles are growing, and as a result of that it becomes non-conducting kind of the thing, and that is why virtual off is there. And ionization current during the T4 time, that means sparking is taking place during this period, and that is why you can see the current is increasing. So we have to measure this, and the total time T is T1 plus T2, T3 plus T3 plus T4, that is the complete cycle time. So these 4 times have been measured. Online transient current measurements. Important phenomena can be understood only by studying the transient current, then only studying the average current. Most of the researchers, they try to measure the average current, which is really not useful when you want to study in depth or scientifically in depth the phenomena of sparking. The transient current waveforms reveal the process complexity and help in understanding the entire time changing phenomena during one complete current cycle of ECSMM, that is time phenomenon means T1, T2, T3 and T4. This study is further extended and carried out for various materials, that is workpiece materials, using different kinds of machining power sources that I have mentioned to you in the earlier lecture also. Power sources, that is a pulsed power sources which may have rectangular pulses, sinusoidal pulses or triangular pulses. Now you can see here transient temperature during micromachining with DC voltage source. These are the transient currents that you can measure here along with the time, and this is the soda line where we made 8 or infinity type of the micro feature. The on time of the pulse is ranging from 0.1 millisecond to 0.5 milliseconds. The time between the 2 consecutive sparks is ranging from less than this one. So this here you can see this is the sparking taking place over here. So the one can measure the time between these 2 sparks, and which is less than 0.5 millisecond, 0.1 to 0.5 milliseconds. So this helps us in studying in depth the process. Transient current during micromachining of glass with HWR, half wave rectified DC voltage source. Now you can see here these are the transient current waves are there, and during 3 to 9 milliseconds of time repetitive sparking is taking place with different time duration and current amplitude. You can see over here around 25 positive and negative pulses are observed during about 7 millisecond time. So you can find out the time for each pulses, and you can see here this is the kind of the structure obtained, and this is the 2 complete and 2 half wave current pulses can be seen of time durations ranging from 0.1 to 0.3 milliseconds. These are the 1 and 2 complete pulses, and this is the half pulse and this is the half pulse. This is just the picture taken which shows these features. The resulting frequency is 2.5 kilohertz to 5 kilohertz. Now you can see over here this part of current plot elaborates the transient nature before and after the sparking. You can see here how this current is varying, here the sparking is taking place. Current measurement while machining soda lime glass and quartz. So you can see another example over here. Current measurement sparking are shown over here. The average process current around 0.1 ampere, a pulse of height of 0.3 ampere can be seen of time period greater than 20 millisecond. A second pulse of instantaneous current value more than 0.4 ampere can be seen after a period of around 15 millisecond. Its time period is about 6 millisecond. Now, you can see here discharge characteristics. Now, the temperature, they are the discharge current range, discharge duration, that is millisecond, discharge repetition rate and frequency, and this is the temperature. You can see here the temperature achieved is 860 to 1100 degree centigrade. Energy associated with each discharge, voltage, average striking current, etc. all these details are given, and average radius of machined area per discharge is 30 microsecond. All this depends upon these machining conditions. So, average striking circular area per discharge again 70,685 micrometer square given over there, and average striking energy density is something like this, 25 into 10 raised to power 6 joules, and average striking energy for metal removal is 548 into 10 raised to power 6 joules. So, we can you can calculate this from these formulae. So, we can try to understand what is happening at different stages in this particular process during sparking. This process has potential for machining in micro regime, that we have already seen. Inferences: the trend for the transient current in DC, HWR, DC, AC, that is alternating current, and pulsating supply sources is similar. Current waveforms show the stochastic and repetitive pattern of the process. It is stochastic in nature, and it depends upon also how the bubbles are generated between the workpiece and the electrode. Electrode may be cathode or the anode, and what is the condition of the surface on the workpiece. Stochastic nature is due to the rate of hydrogen gas generation, bubbles formation, sparking rate, sparking energy, and other factors. The repetitiveness is due to the sequential formation of various phases in a single spark cycle. Now, here deliberately it has been mentioned single spark cycle. I will show you its importance later on. Transient temperature measurement methodology, this is another important phenomena, because the material removal is due to the thermal process, that is the heating that results in melting and vaporization and flushing out of the molten material from the gap. So, it is very important to know what are the temperatures at different locations. This will help us in improving the process later on. Transient temperature measurement methodology: in situ transient synchronized temperature and current measurements were performed for the first time in ECSM, especially in the machining zone. Current measurement we have already discussed. Now, we will see the temperature measurement. Transient temperature measurement: pyrometer was used for this purpose, measurement of transient temperature of localized zone on the workpiece surface in a non-intrusive way. Then K-type thermocouples were used to measure the temperature on the workpiece surface. Immersion thermocouples were also used to measure the temperature of the electrolyte in the cell. And then temperature transient current measurement, that is resistive shunt method, was used. So, you can see three different types of the thermocouples are used for measuring the temperature at different locations. Temperature sensing plant: pyrometer is focused at the center of the workpiece where discharge strikes the workpiece. Two K-type thermocouples are placed at T1 and T2 positions respectively, 4 millimeter and 10 millimeter away from the discharge location. So, please note it carefully, 4 millimeter and 10 millimeter are far away from the discharge location, and we will see how temperature variation is taking place at the discharge location and at T1 and T2. You can see here carefully. Now this is the discharge location, this is the T1 temperature, this is 4 millimeter away and this is 10 millimeter away from the discharge location. We are assuming that this is the discharge location. This discharge location depends upon where the sparking is taking place, which is stochastic in nature, which we have already mentioned in the assumption while analyzing it. Measurement problems. Transient, that is millisecond order, and localized area of 1 millimeter square, nature of temperature where discharge strikes on the workpiece surface at point 1, presence of electrolyte, noise due to the electrical discharge, wide temperature ranges involved on the workpiece. So, these are the problems which really do not permit to very accurately measure the temperature during the process. Few thousands of degree centigrade at point 1. Point 1 is the one where this discharge is taking place. Few tens of degree centigrade at 2. Now, you can see here this is the 2 and this is the 1, and in the electrolyte cell few tens of degree centigrade at 3 and 4, that is not shown over here. Here it will be shown. You can see here this is the 1 where the sparking is taking place, this is the 2 the few tens of degree centigrade are here, and this is 3 electrolyte and this is again the electrolyte. So, it is not connected with this one, these 1, 2, 3, 4 are connected with this particular figure. So, you can see it, and there are many problems as mentioned over here during the measurement of the temperature. The pyrometer was modified for transient temperature measurements. Its response time was experimentally determined and it was found to be less than 1 millisecond, because this is very important, because temperature changes very fast with time. And K-type thermocouples are fabricated with a smaller bead diameter to ensure a smaller thermal mass and hence faster response. Immersion thermocouples with a special coating to withstand harsh environment in the electrolyte. This is very important coating, otherwise thermocouple itself will get damaged. Measurement uncertainties. Again, this will tell you the limitations of the measurement process. Uncertainties in the measurement arise due to the change in location of the discharge, because it is not fixed where the discharge is really taking place. So, it will help us to remove this or to minimize this problem by taking a smaller and a smaller size of the tip of the tool or the electrode where you are measuring the temperature. Different energy associated in each discharge, blockade of the workpiece surface from the pyrometer, absorption and fast quenching due to electrolyte, because heat is absorbed and electrolyte is there. So, quenching is also taking place. This also affects the temperature measurements. And change in emissivity of different medium, because with temperature emissivity of the medium changes, hence that also affects the temperature measurement. And the trigger movement of oscilloscope. So, you can see here sharp rise is there, this is the 5 milliseconds and sharp rise is there, and here the temperature measured is around 1500 degree centigrade, and this temperature is good enough for melting and even vaporizing many materials. Open pulse showing higher temperature of the order of melting point of the workpiece material. Synchronous transient temperature and current results. You can see here this is the current waves and this is the temperature rise at that particular location, and definitely here is the sparking taking place, measurement takes certain time. So, here is the measurement of the temperature. Time synchronized current and ensuing temperature rise of the workpiece for copper and tantalum. Discharge occurs in short bursts. An instantaneous rise in the temperature in a localized region. You can see here, this is the current wave and this is the temperature one. Temperature, and there is the instantaneous rise in the temperature as sparking is taking place. Temperature rises to 1640 degrees centigrade in this particular case. Conclusions. In situ transient temperatures have been successfully measured for the first time during the ECSM, and you can also call as ECSMM processes using a pyrometer. The correlation between the transient current and temperature has been experimentally established. We have seen here, this is the current, this is the temperature. We can find out at what difference of time the temperature rise is taking place, because all this phenomena of conduction convection take time. Working surface temperature or workpiece surface temperature is greater than or around 1700 degrees centigrade just after the current pulse strikes it, few milliseconds or so. Maximum temperature is attained within a fraction of milliseconds and remains there for about a few milliseconds, and that you can see here temperature is remaining for certain period over here. A pyrometer with a higher temperature range, say 900 to 3000 degrees centigrade, would measure it more precisely. So, one can think of taking a better pyrometer to measure the temperature more accurately and more precisely. Inferences. Synchronized time varying current and temperature study reveals that the discharge in ECSM is similar to the discharge in a gas due to the application of high electric field as proposed by Jain and Pandey. The electrons generated in a huge number due to the discharge accelerate towards the workpiece kept near the cathode. This flow of large number of electrons is seen as a current spike for a short duration of a few milliseconds. This bombardment of electrons raises the temperature of the workpiece momentarily, giving rise to a sharp temperature pulse as seen in the previous slide. Now, here I will like to mention that these electrons which are emitting, they move towards the workpiece at a very high velocity, and due to the kinetic energy they raise the temperature of the workpiece to very high value at which it can melt and even vaporize, and this was proposed by Jain and Pandey that the temperature can be few thousand degrees centigrade theoretically. The temperature reaches to melting and evaporation points and material removal takes place. Melting and or vaporization is the main mechanism of material removal in case of electrochemical spark micromachining and electrochemical spark machining processes. Potential applications of ECSMM process. The process has potential uses in several areas such as machining of micro holes, micro channels, micro filters, micro seam welding of copper plates and foils. This is very important that a new area of application like welding is being proposed, and heat treatment, surface modifications can also be done by this particular process. Areas which require further research activities for industrial acceptance. Feasibility study in different areas, transient temperature and current study, experimental measurement and theoretical estimation of temperature. This is very important, because if you want to refine the process and you want to make a process better, then theoretical studies are very important for that purpose. development of semi-automatic experimental setup that will also help in improving the performance of the process. Development of novel metrology technique, I have already discussed how you can measure and study the micro features by taking the inverse replica with the help of PDMS or other materials, and study of process performance for different materials. We have conducted the experiments, or researchers have conducted the experiments on the very limited type of workpiece materials. This can be explored further depending upon the requirement. Different power sources, we have already discussed 3 types of pulse power sources being used in ECS process, that is the rectangular, sinusoidal and triangular pulses. Different machined features can also be explored, and deposition with electrochemical sparks, hybrid microfabrication, upgradation of the setup with built-in metrology facility. This is very important. Lot of improvements can be done in the fabrication of the setup, especially by incorporating built-in metrology facility, so that you can check what kind of the features are being prepared, and later on you can improve upon it by varying the machining conditions and optimizing the process. Thank you very much.